section, we are going to not only calculate the enthalpy change or the heat change, but we're also going to pay attention as to what this heat change is coming from. And so we're going to look closer at our phase changes. And so they all have different names, which we already know that. But we're also going to, just like we did in the lab, that was called the heat of fusion. Each phase change, that enthalpy change that goes along with it, has a different name. So here we go. You do need to know these because if it just asks for the heat of fusion, you need to know, okay, well, what is that from? So the first one is heat of fusion. Okay, it's the heat absorbed when something is melting, going from a solid to a liquid. Now here, if you don't have down pat your phase changes, that melting is from a solid to a liquid, you need to get that down pat during this section as well. I feel like some of you do. Now the weirdest thing is to think about that during that phase change there is not a temperature change. And this is something that is going to take a little bit of getting used to, because you think about melting because the solid is getting warmer. But the truth is the temperature change has gotten warmer to a point, and at that point the melting happens. Okay, so during these actual phase changes, there is not a temperature change. And so that makes these equations shorter. But trust me, when you get into it, you're going to think, well, what's the temperature change? But there is not. It's happening at a certain temperature, so you don't have a delta T. So your heat is your moles times your delta H of fusion. And you have a table for these, I believe, on page on page 522. Oh, okay. The opposite of melting, the opposite of going from a solid to a liquid, would be going from a liquid to a solid. Now, we tend to use the word freezing, but technically it would be solidifying. Okay? And so that's going to be a delta H, and then it will have solid as the subscript. And if you look at your chart, you will find that these two are opposite of each other as far as positive and negative. Again, you're just taking your moles times that delta H of solidification value that you're going to find on that table, and then that gives you your heat lost. So look at the heat of fusion is heat absorbed, and then your heat of solidification is heat lost. And those two are going to be opposite of each other. Remember your little catchphrase from that lab the other day. The heat absorbed is equal to the heat lost. Okay, so those two go hand in hand. They're like little partners. I think it just says moles. I'm not worried about that. Okay, this is what I just said, but if you want to write it out, the heat absorbed by melting is equal to the heat lost when the liquid solidifies. So the delta H of fusion is going to be equal to a negative delta H of solidification. They are opposite of each other. So if you look at that table, you'll notice that it just has the heat of fusion on it, and it doesn't have a heat of solidification. That's because you're supposed to know that the heat of fusion, or the heat of solidification, is opposite. So it's not going to list it on there. you're going to need to know if it's asking for the delta H of solidification that you just use the fusion but put a negative sign in front of it. Okay, we're going to get to that practice here in a minute. Your other pair of heats is when we go from a liquid to a gas. That is vaporization. And so the amount of heat necessary to vaporize 1 mole of a liquid is your delta H with a vape at the bottom. Still no temperature change. We've talked about this as far as a boiling point. At that point, the liquid turns into a gas, but there's not actually a change in temperature while that phase change is occurring. So there is no delta T. Okay, so this one has an opposite as well. And its opposite is condensation. So condensation is the opposite of vaporization. We're going from a vapor condensing to a liquid. And so the little subscript is COND for condensation. Again, no temperature change. Just moles, but you're not going to find that value on the chart. You'll just have to use the opposite of the delta H for vaporization. So you need to know which two go together. Otherwise you might get very far off track. Okay, so there it is. The delta H of vaporization is equal to the negative of the delta H of condensation. They are opposite processes. So for any of these calculations, if you're not in moles, you need to get to moles. Okay, so that's using the molar mass calculation, that's easy. And then you are looking it up on the chart as far as your delta H. Now there's going to be some values that you're going to be using a lot, and you'll start to be comfortable with them, especially water. So if you look at that chart, it gives you water and some other ones, but we're going to be using water the most. And if you look at that chart, there's a large value for water as far as the delta H of vaporization. We know that water values are usually very far off of any other substance. We'll be using water the most. Burn yourself with sweet. Now for these, you can write a balanced equation, except it's the same substance, just a phase change. So your reaction is going to look very simple. So this would be the reaction for condensation. And that 40.7, you're going to be using that number a lot. So let's do an example. I hate these examples because you can't even see what it is. I'm not worried about heat curves just yet. Okay, let's try this example even though I can barely read it. So it'll say how much heat, again we're solving for Q or delta H, how much heat is absorbed when we have 24.8 grams of water, liquid water, at 100 degrees Celsius and 101.3 kPa, and it's converted to steam at 100 degrees Celsius. All of that Celsius and kPa is in there just to mess with your head. It is telling you that we have liquid water converting to steam. Okay, so that is vaporization. So all we need to do is take that 24.8, get it into moles. That's easy enough. And then multiply that moles by the delta H for vaporization value, which is 40.7 kilojoules. And that's all you need to do. So once you know what phase change is occurring, the math is very simple. Very simple.